Okay, cool.
Yes.
So I'm going to talk about this work that was published last year. It was done in collaboration with my colleagues, Nina, Nicolas, and Joao. So the work is titled From Contrastive to Abductive Explanations and Back Again. So at the beginning, a bit of motivation. We all know that we've been living in the age of what's called ML revolution. ML is ubiquitous in modern life, and there are lots of amazing successes, like self-driving cars come to reality. We all have smart assistants in our phones, and so on and so on. And at the same time, this is a meme, by the way. It's not my opinion. It's just a funny meme I wanted to show you. So in some cases, machine learning algorithms fail, right? And in safety critical applications, it's really important. Which brings us to the issue of explainable AI. In explainable AI, I have a system, a classification problem, for example, which a classifier gives you an answer. This is the current status quo, and what we want in explainable AI is we want to get explanations that attribute responsibilities for the prediction to some features, not everything, right? So we want to get explanations, for example, why this image is a cat, right? Let me first define what we call formal explanations. So here we consider the standard classification scenario where we say that the classifier computes a total function that maps an instance from the feature space to a class of some class of some set K, and so an instance V is mapped to some class, right? And an abductive explanation is a subset of features that is sufficient for the prediction, right? So we say that these features take this value that are equal to the values in the instance, and everything else can take any value, and the prediction is not going to change, right? So this helps us answer a why question. Why this prediction, right? Somewhat dually, there is a concept of contrastive explanation, which we study in this work, which basically is a subset of features that, if allowed to take any value, then there will be an instance in the feature space that is predicted differently than C, right? So this kind of explanations helps us answer a why not question. And this is what this paper was about. So I have a couple of examples. Let's say we have 5 features and binary classification, 2 classes. And this is our model. It's a very simple decision list, right? Say we have an instance where everything is assigned to 1. And if you look at the decision list, you can see that the prediction is negative. If you examine the decision list, it's easy to see that it's enough to assign x1 and x2 to 1, and the prediction is not going to change, right? Because the first rule fires. It's not that easy to see, but still valid, that feature 3, if assigned to 1, also entails the prediction negative, right? Because otherwise, I mean, if x3 is 1, then the second rule doesn't fire, it's for sure, right? Similarly, we can see that it's enough to allow 1 and 3 take any values, and then we are guaranteed that, we're not guaranteed, but it's possible to reach the misclassification if the second rule fires. What we also showed in this paper is the following nice results. Say we have these 2 abductive explanations, each of size 2, and they share a literal, the red one. Okay, given this set of abductive explanations, we can actually construct constructive explanations by what we call the hitting set duality. What we want to say here is that each abductive explanation is a minimal hitting set of all contrastive explanations, and the other way around, right? If you look here in this image, you can see that the red literal is shared. So to hit these 2 AXPs, it's enough to pick just this single literal, and that will comprise one of the contrastive explanations, and the other one would be to take the other 2 literals from abductive explanations. Right. We also proposed a way to compute abductive explanations. Same example, same decision list. Same instance, and so we want to answer why not plus, right? The algorithm is very simple, so it's a linear search procedure. At every iteration, we try to drop a literal and check if the CXP condition holds. Here we try to drop 1. Is it still possible to reach misclassification? Yes. Is it possible to drop 2 and still reach misclassification? Well, no. And we continue doing so until we get a subset minimal contrastive explanation. Okay. We also showed that both abductive and contrastive explanations can be enumerated exhaustively using this algorithm, which is based on the implicit hitting set enumeration paradigm. There are families of algorithms that are very similar to this in other contexts. This is just another one. It's based on the duality, right? And to conclude, I don't have much time to conclude. This work to the best of my knowledge, first defined formally what contrastive explanations are, similar to abductive explanations. We also discovered and proved the minimal heating set duality between CXPs and AXPs, which can be used in the explanation enumeration algorithms, as I showed on the previous slide. And it can also be used in solving membership problems. And both of these proved helpful in several of our papers this year. For example, in the second paper, in the paper that was presented second in this session. Okay. In the paper, we also have two experiments, and the first one was to enumerate all explanations exhaustively and to show that it actually scales for medium-sized boosted trees. The second experiment was to enumerate only CXPs and then to look at the features that are included in CXPs. And it turned out that these features that occur in small CXPs, they are actually features that are reported as explanations by a heuristic explainer, SHAP. It's a very well-known explainer. So enumerating CXPs actually helps us understand what SHAP is actually doing. Okay, so if you're interested, please check out our paper. Meanwhile, I can ask questions if there are any. Thank you.